And this is 5C6. I believe it's our last problem, at least the last one that I will do. Not sure though. I have two pucks, M1 and M2, and they have velocity V1 and V2 relative to the center of mass. It's very important. It's not relative to my lab, it's relative to the center of mass. So, here is the center of mass. I am moving with the center of mass frame of reference, and so I have one particle, M1, coming in like this, velocity V1, and I have a particle like this coming in with V2. And here is my mass M1, and here is my mass M2. When you're working in the frame of reference of the center of mass, think about it, the particles always must both come to you if you have two, or they must both go away from you, or they must be stuck at the center of mass. That's also possible. That is absolutely necessary, otherwise the net momentum could not be zero. Think about that. So this is one such situation. Now, of course, the center of mass itself could be moving relative to my laboratory frame. This is what you will see in the reference frame of the center of mass. What you will see in the laboratory frame is something entirely different, and I will get back to that at the end of this problem. Now, there is a collision. And after the collision, the momentum must again be zero relative to the center of mass. So let's assume that after the collision, that M2 moves out with velocity V2 prime, and M1 moves out with V1 prime. As I said, they must either go away from the center of mass, or they must go to the center of mass, or they must be stuck at the center of mass. There's no other possibility, because the momentum relative to the center of mass frame of reference is always zero. So I can write down now that M1, V1, this is a momentum vector, plus M2, V2 must be zero, and this is also M1, V1 prime, plus M2, V2 prime. This is the conservation of momentum, but it is zero. I can introduce a sign convention. I've done that before. I call this plus, I call this negative, and let me call this plus, and let me call this negative. And when I do that, I can rewrite this as M1 V1 minus M2 V2, that is 0, and that is M1 V1 prime minus M2 V2 prime. Remember, when you solve this, that V2 is larger than 0. It is the speed, but I already know that it is coming in like that. Keep that in mind. All these numbers will be positive, but the direction is non-negotiable. The direction of this one will be in this direction, and the direction of this one will be in this direction. Can I solve for V1 prime and V2 prime? No, you can't. The best way to see that is that if V1 prime equals V2 prime equals 0, that would completely satisfy this equation. And why not? Why would it not be possible that when these two objects hit each other like two pieces of putty, that they get stuck together right at the center of mass, and that's it, and they stay there? That's certainly one possible solution. So there's no way that you can solve for V1 prime and V2 prime unless you know more. And you do know more, you're being told that the collision is also elastic. That means that the kinetic energy is conserved. And if kinetic energy is conserved, then you have another equation at your exposure, and you can write that down, no doubt. You have 1/2 m1 v1 squared plus 1/2 m2 v2 squared equals, and you write down the kinetic energy after the collision. And if now you solve the combination of conservation of kinetic energy with this equation, which is the momentum conservation, then you will find, after a little bit of massaging, that the magnitude of V1 prime is V1, and that the magnitude of V2 prime equals V2. In other words, the speeds have not changed, but the directions have changed, and you have no information about those directions. Does it mean that nature has a free choice about the directions? Well, not quite. Suppose you have two marbles that approach each other and hit each other. Well, then, as you can see, it is important to know exactly how they hit. We call that the impact parameter. If they hit a little bit not exactly at the center, then you get a different direction that they move away from each other than if they hit head-on. That information we are not being given, and so I will not discuss that any further. But now I will come back to the question, what do I see in the frame of reference of my laboratory? And for that, I have to add now the velocity of the center of mass in the laboratory. And let's assume that the velocity of the center of mass in my laboratory is like this. So all these velocities have to be added to this one, to the center of mass, and to this one. So what do I see from my laboratory? I see the vectorial sum of these two. So I see this particle flying in this direction relative to my laboratory. And I would see this particle flying in this direction relative to my laboratory, and they will collide right here. That's all I will see. They will collide here. And by that time, the center of mass has exactly reached that point. What will I see after the collision? Well, I have to add that same, exactly that same velocity vector of the center of mass. That velocity vector has not changed because there are no external forces. And so I have to add this vector and this velocity vector to all these 3 points. And so what do I see? This is the velocity after the collision of particle 2. And this is the velocity after the collision of particle number 2. And so what has happened is they came together like this. Bingo! They hit somewhere here. And then they do that. That's what you see in your laboratory frame. They come together and do this. However, in your center of mass frame of reference, they come together like this, and then afterwards, all of a sudden, you see this. Or they stick together. Very interesting, and we very often use the center of mass in order to shorten a particular problem. The collisions is elastic. Therefore, kinetic energy is conserved in the frame of reference of my laboratory. But I have used the conservation of kinetic energy as seen from my frame of reference of the center of mass. Is that allowed? Did I not cheat? No, I didn't. Convince yourself that if kinetic energy is conserved relative to my laboratory, that it's also conserved relative to the center of mass. Keep in mind that there are no external forces on these two objects, so the center of mass relative to my laboratory has a constant velocity and will always keep that constant velocity. And that will very quickly lead you to the answer why what I did is totally allowed.